Hello, welcome to our presentation of indoor air pollution forecasting using deep neural networks. Thank you for attending. We found that there is an increasing concern regarding the air quality in indoor spaces because we spend a lot of time there. And we found that although there is previous work as described on the paper, there is a lack of published open source models, or it doesn't include too much technical detail to re-implement it. So our paper tries to address those forecasting indoor air quality in indoor spaces using an open research, open source, and open data approach, but also to do some decision making based on data. Our data sources were three: the indoor air quality sensors, that included 6.2 million records. It was recorded every 3 seconds into a CSV file, and it was stored into a Raspberry that was on our home. The air quality monitoring of the government, it had 2.3 thousand records, and it has a resolution of every 1 hour, and we downloaded those files individually in a manual fashion because there was no API available to do it automatically or in a scripted fashion. The open weather map, it's a data source. We acquired that data, and it includes the weather and atmospheric details for every 1 hour with 5,000 records. We download it from the website using the CSV file. And we have 15 different variables that were fed into the model, all the models we had, especially the temperature, the pollutants, the humidity, the atmospheric pressure, and we binded together, collated that data of those different sources using the date as our primary key, and we tried to predict the indoor air quality, which is an index created by the EPA, which it has values between 0 to 500, with 500 being the worst quality and 0 being the cleanest air. We did some exploratory data analysis of the sensor and found that we had only around 1% of missing data. It was because of power outages and software updates, reboots of the Raspberry. We didn't find that to be pretty much problematic. Then we did the EDA on the government data, but we found too many gaps, as you can see on the right side plot. Then we tried to address it with different sources. Fortunately for us, there are within 10 kilometers radius, at least a few other monitoring stations with different missing data numbers. On this next slide, you can see the percentage of the missing records by pollutant. It varies widely, as you can see. It depends even by the pollutant on each or every air monitoring station. We found it that most of them have more than 15% of missing data, which is a lot. It will be very difficult to handle. But fortunately for us, as you can see on the right side plot, we found that La Merced on most pollutants except NO had very few missing data on those. So we used that as our main outdoor air pollutant data source. On the weather data we also did the EDA, and we didn't find any missing data points, fortunately. We only found that it was a little bit weird, the distribution of the data, a little bit skewed. but we didn't find any other problematic issues on that source. We implemented the data preprocessing because it was very important for us to treat all the data as a time series or a sequential data. And we divided, for example, the test and train data sets using 30 and 70% respectively. And we avoided shuffling that data. And we aggregated all data, as I said, with the date as our primary key. Then we moved the data, the sensor data and the government data, and tried to address those missing records. We explored different data imputation approaches, the KNN, generalized linear methods, Bayesian, GLM, but we found that the best approach was the linear interpolation because of interpretability. Also, we added some noise into it because we wanted to avoid any kind of overfitting into our deep learning models. As usual, we did some use of scalars because we had different variables in very different scales. We also did some time series processing because we needed to capture that history, and we used the built-in Keras time series from data source, and it created us some history windows, transforming the two-dimensional matrices or data frames into tensors with that history as the additional dimension. We implemented different neural networks architectures and compared them. First, we started with the perceptron because it's a fast training. It's also the base of the rest of the neural types. We found it to be a very competitive performance. Then we tried the convolutional one dimension because it's usually with a good performance, but we found it to be a little bit more noisy and more unreliable on the results. And it also has a high processing of resources and usage on the GPU. We then tried the long short-term memory. It has a very, very robust performance, and it was also very high, of course, on the memory, but it was very reliable overall. Obviously, we found that each architecture had its downsides. Then we tried to combine those architectures into a single model. Of course, we expected better results, but as you can see on the right side table, the results were more favorable to other types. It was also more complex to code or to model it, but overall it was very, very useful experiment because we also found that it was very easy to train it. We didn't run into too many out of memory issues as many GPU practicers find. As you can see on this slide, on the left side plot, the LSTM 00, which has 4 weeks of history, it was the best performer. Also, we found that during the hyperparameter tuning, the stride of 2, that is skipping one record for every other on the history, benefited it. So we also found a better performance on the simpler networks such as DNN, LSTM, instead of convolutional or that combined model with different architectures or types of neurons called BEST01A. So it was very surprisingly to find that the convolutional networks didn't perform as well as the baseline model. That is a suggestion from Keras tutorial and also from TensorFlow tutorial on time series to have a baseline with a single perceptron architecture and having no activation function. That was surprising for us, as I said. Conclusions, we found that it was very useful to combine those data sources because the models need to be fed with more data. We also found that it is possible to improve the performance combining that data, but also using data engineering techniques and also using some computer science techniques, such as the cloud computing, because we found it to be easier to use the cloud using scripting models to compare and do that training in an unattended fashion. And it was also very repeatable because it was the same script, right? So we invested a bit of time not only on the architecture and the complex modeling, but also on the scripting for doing that in a very replicable fashion. We think there is also, of course, more further research, especially if we have more data. We are still collecting that data, and we will try to publish it as soon as we reach the 2 years of capturing that pollution or indoor air quality. We also plan on doing some transfer learning approach for this time series data. It has been useful on, for example, image data or video data and sound. We think it can be useful for this type of data. We also would like to create a larger model and feeding it with more historic data, because if you have a very large model, it needs to be fed, of course, with more variables or other data sources. Thank you very much. Please post any question you have on the chat. We're ready to answer them. You may also visit the GitHub repository scanning that QR code where you can find the data, the source code, and also the paper. Thank you very much.